Okay, this is me going over question 7 to the best of my ability. And so for part 1, we're adding peroxy acid, MCPBA, which is a peroxy acid. And peroxy acids lead to the creation of epoxides. The mechanism is very complicated. It's something weird like uh, RCO like H. And well, you don't need to know this like all this, I think. What you need to do is to figure out that this oxygen right here is gonna become basically like alone and like very weakly related to all this because it's made a partial bond here, and then OO relationships aren't really stable. It's really, really weird. Basically, what ends up happening is that this oxygen ends up forming an epoxide somewhere here, um, because somehow like this is more stable than what it was in before in the peroxy acid, and this simply just promotes the formation of the epoxide, which gives the first answer. And um, in the answer key, it indicated that this was like on a wedge and this was on a dash. But I don't think this really makes sense because even though the formation of epoxides uh, is an SN2 reaction, there really is no way to determine the exact stereochemistry because this isn't really indicated by anything. So I think I just wanted to show that there's like a difference here along the lines. Um, but the exact stereochemistry can't be determined, possibly. And so for right here, we have, let me draw what we have here briefly, right? And basically here adding um, this under acidic conditions. And obviously this epoxide ring is going to have to break. So what's going to happen is that the ring breaks here. Oops. And you end up with OH, the H coming from the methanol or the hydrogen in the solution. But what I think is more likely is that it's probably just going to be this, oops, right, just that, this, going to take on that, giving this, and this leaves, of course, the epoxide, which is a very, very strong base, and it's going to go, I mean, it's a very strong base, and because this has the charge there now, it's going to go right there, and form the methoxide little thing. And it's important to note that because this is an acidic solution, the OH ends up on the less substituted carbon, whereas the methoxide ion ends up on the more substituted. This only occurs in acidic solutions. If this were basic or neutral, then the methoxide ion would end up on the less substituted and the hydroxide on the more substituted. Why exactly? I don't know, but that's the way it is, right? And so now that you have like this, now that you have this molecule here, you add an H2SO4 and H3PO4. So if you and we add heat, and so if you look at the molecule we have here, we can notice that there really isn't much we can do with it. There's no like real good leaving groups. There's no alkenes. And so while the addition of H2SO4 and heat might indicate in Williamson's ether synthesis, we have nothing to work with to produce an ether. So it's not going to be that. So in this case, it's really just going to be like weird SN2, E2, SN1, E1 kind of uh, rearrangements. And honestly, I'm not exactly sure if I would have gotten this without looking at the answer. But the reason I can come up with as to why it ends up being this is because the H2OH is the closest thing we're gonna have to creating a leaving group, right? So when we add in H2S, blah blah blah, the OH here is gonna act as a nucleophile. It's gonna take this here and it's gonna form H2O, and then the R group is gonna be plus charge. And this is going to produce a very good leaving group because this is going to become water once it comes out. It's going to be stable. And it also produces a conjugate base, which is a weak base. And this combination of a good leaving group and a weak base or nucleophile is going to lead to the E1 reaction, where this leaving group is just going to come off because it's much more stable that way. It's going to produce the intermediate carbocation right here, and you're going to have the intermediate weak acid of HSO4 or H3PO4, whichever one, H3PO4, and this H atom here is going to get taken in right there, and this is going to promote the E reaction where you kind of form the double bond here and stabilize everything. And of course, these things are still up here. The reason why we take the the hydroxide ion that was here instead of the methoxide is because the hydroxide is more likely to form a strong leaving group in the water molecule, whereas methoxide really isn't going to be that good of a leaving group even if you add oxygen to it. It's not favorable at all. And also, we can't do much with the methoxide because it has to be for the future answers. So, use your brain. For the subsequent reaction here, this one's pretty straightforward. You just have an hydromercuration, or whatever, you're adding mercury to it. You have all the same solvents with the THF and the sodium boron tetrahydride. I don't know what the actual name is, but you have all the solvents needed, and it's very simple. Whenever you have this reaction, all you do is that you just break the alkene and you add OH as well as an H, and this is going to be following Markovnikov's rule, where the OH is going to end up on the more substituted carbon, which is right here, and the H is going to end up on the less substituted, which is right here. So that leads us to this answer right here. If we look, and if this makes sense here, because we add PBr is going to add a bromine to the OH where it once was. I don't know what the name is, but it makes sense that happens. And for part E took me so long to understand, and I finally figured out why. Basically what we have here is this molecule, and what seems logical is to have the alkyl halide bond right here, for the bromine is going to be the leaving group indicated by this. And we have a tertiary alkyl halide of that. And that automatically makes things a bit weird because this suggests that it's only possible to have either the SN1 E1 or E2. And so if we look at what we have here, all we're doing is we're just adding the N3. We're not making any double bonds. So this has to be an SN1 reaction. And SN1 reactions with tertiary alkyl halides require either a protic or a protic solvent, right? However, in a protic solvent, E1 is favored. So ideally you would use a protic solvent. However, the answer is DMF, or acetone, which is aprotic. So that's weird. And if you look at the N3 here, the only way N3 could be a nucleophile is with the addition of like a metal, right? And like a sodium, which they use here in order to kind of explain how this is going to break off, and you have like a nucleophile here in the end. So that makes sense, right? You want something that's going to produce like that's going to lead to like the bare exposure of um of electrons, making a good nucleophile. It's just a matter of the solvent. I would personally believe that it would be protic solvent, which would promote the SN1 reaction over the EAT1. And I checked on Piazza, and somebody asked a question about this. And Professor Hunter said that this was an oopsie. I don't know which professor it was, but they said this is a really good catch and honestly a big oops on our part. So that's exciting. He said this would be a better question if the nucleophile was weaker, because this is a very strong nucleophile with the exposed electrons, or if the substrate wasn't tertiary, right? Because this tertiary limits a lot of these options by not allowing the SN2 reaction and only allowing the SN1, which requires very specific conditions. Um, and honestly, even if it was protic, it would still be kind of difficult to kind of lead to kind of the bonding there with SN2. So this part is just a verified question, and DMF is not. It's not a good answer. It's just not. So it's not anyone's fault. It's not our fault that it sucks. It's the professor. So yeah, that's my explanation for this. Um, Hopefully this makes sense. Ask any other questions on this. Good night.